In this session, we shall discuss about the frequency response of the op-amp. The frequency response of the op-amp is defined as the variation of the gain of the operational amplifier with respect to frequency, and it is divided into two categories because gain is a complex quantity. One, magnitude response, and it is defined as the variation of the magnitude of the op-amp with respect to frequency, and second one is phase response. It is the variation of the phase of the gain of the op-amp with respect to frequency, and depending upon the loop connections we divide the frequency response once again into two categories. One, the frequency response of the open loop op-amp, and two, the frequency response of the closed loop op-amp. First of all, let us consider the frequency response of the open loop op-amp. The equivalent circuit of practical op-amp at high frequencies is as shown in figure 1. In this figure, all the capacitance effects are represented by a single capacitor C across the output terminals, and this capacitance with a output resistance of the op-amp form a low pass network, and hence for a fixed input voltage output decreases as frequency increases, that is gain decreases at 6 dB per octave or 20 dB per decade. Here decade represents 10-fold increase in frequency, whereas an octave represents 2-fold increase in frequency. The open loop output voltage of the op-amp is given by V0 equal to minus JXC by R0 minus JXC into AOL into VID. Here XC is equal to 1 by 2 pi FC. This minus JXC represents the reactance of the capacitor, and AOL is the open loop voltage gain, and VID is the input differential voltage. At DC, that is at 0 Hz, the capacitor acts as an open circuit. Now the open loop voltage gain at high frequencies is influenced by the capacitor, and it is given by A equal to V0 by VID equal to minus JXC by R0 minus JXC into AOL. Substituting XC equal to 1 by 2 pi FC in the above equation, we get A equal to AOL by 1 plus J 2 pi F R0 C, that is A equal to AOL by 1 plus JF by F1, where F1 equal to 1 by 2 pi R0 C. It is called the 3 dB cutoff frequency or corner frequency or break frequency of the op-amp. From the above equation, we find that gain is a complex quantity. So its phase angle and magnitude are given by magnitude of the gain given by mod A equal to A by root of 1 plus F by F1 whole square, and its phase angle is equal to minus tan inverse f by f1. Both phase angle and magnitude are functions of frequencies as shown in figure 2. At f very less than f1, the capacitor effect is negligible and hence mod A equal to mod AOL. At f equal to f1, mod A in dB equal to mod AOL in dB minus 3 dB, and phase angle at f equal to f1 equal to minus 45 degrees. At f very greater than f1, mod A decreases at a rate of 20 dB per decade. The unity gain bandwidth ft is defined as the frequency at which mod A equal to 1. So, substituting mod A equal to 1 for f equal to ft, we get ft equal to AOL f1, and this is achieved by neglecting 1 because AOL is very greater than 1. In typical data sheets of the op-amp, we get only the value of the unity gain bandwidth, that is ft, but we won't get any value for 3 dB crossover frequency, and hence the 3 dB corner frequency is determined from the above expression. From the above expression, we get 3 dB cutoff frequency f1 equal to ft by AOL. Open loop configuration is rarely used because of its high gain, and negative feedback is used to reduce the gain to a desirable value. Now we have to consider the effect of the feedback on open loop gain and the frequency response of the closed loop op amp. Let us consider the non-inverting op amp as shown in figure. The open loop gain of the op amp at high frequencies is given by A equal to AOL by 1 plus JF by F1, where AOL equal to the open loop gain of the DC input signal, that is at F equal to 0, F1 equal to 3 dB cutoff frequency, that equal to 1 by 2 pi R naught C, and F equal to operating signal frequency. A can be modified as A equal to AOL by 1 plus j omega by omega 1, that equal to AOL by 1 plus S by omega 1, where omega equal to 2 pi f, omega 1 equal to 2 pi f1, S equal to j omega. This is the Laplacian operator. Therefore, V naught equal to AOL VID by 1 plus S by omega 1, since A equal to V naught by VID. The controlled source AOL VID by 1 plus S by omega 1 in figure 3C depends on frequency of operation. The voltage gain of practical non-inverting op amp for DC input signal, that is at F equal to 0 Hz, is given by AV naught equal to AOL into R1 plus R2 by 1 plus AOL into R1 plus R2 plus R0. Neglecting R0 and replacing AOL by A to get the high frequency effect, the closed loop gain becomes AV equal to A into R1 plus R2 by 1 plus A into R1 plus R2, where AV is the closed loop gain of the op amp at high frequencies. Substituting A equal to AOL by 1 plus S by omega 1 in the above equation, we get AV equal to AOL into R1 plus R2 by 1 plus S by omega 1 divided by R1 into 1 plus AOL by 1 plus s by omega 1 plus R2. After simplification, we get AV equal to AV naught by 1 plus s by omega 1c, where AV naught is equal to AOL into R1 plus R2 by R1 into 1 plus AOL plus R2, and omega 1c equal to omega 1 into R1 into 1 plus AOL plus R2 by R1 plus R2. That is F1c equal to F1 into R1 into 1 plus AOL plus R2 by R1 plus R2. Here AV naught represents closed loop voltage gain for DC input. F1c is the break frequency or 3 dB cutoff frequency for closed loop non-inverting op amp. F1 is the break frequency of open loop non-inverting op amp. Since AOL is very greater than 1, the expressions for AV naught and F1c can be simplified to AV naught equal to 1 plus R2 by R1 and F1c equal to F1 AOL by AV naught, that equal to Ft by AV naught, where Ft equal to F1 into AOL is the unity gain bandwidth of the open loop op amp. Now let us compare the 3 dB frequency in case of open loop op amp and the 3 dB frequency in case of closed loop op amp by considering an example. Let us consider the op amp 741C. For this 741C op amp, Ft equal to 1 MHz and F1 equal to 5 Hz. Now let AV naught equal to 10. Then F1c equal to Ft by AV naught becomes 100 kHz. That is F1c is very greater than F1 as shown in figure. The circuit is said to be stable if its output reaches a finite value within a finite interval of time, and it is said to be unstable if it increases indefinitely with time. As shown in figure, a typical closed loop system represents a negative feedback, and here A represents the open loop gain of the op amp and beta represents the feedback factor, beta equal to R1 by R1 plus R2. The gain of the negative feedback system is given by AF equal to A by 1 plus A beta. The feedback amplifier is stable if it satisfies the criteria shown below, that is 1 mod A beta must be less than 1 and 2 angle A beta must be less than 180 degrees. If the gain mod A beta is less than 1 when angle A beta equal to 180 degrees, then the system becomes stable. Bode plots are used to determine the stability of the system. So far we considered an op amp with one break frequency, that is all the capacitors existing in the op amp are clubbed up and they are represented by a single capacitor, and it provides a phase angle not more than 90 degrees and it is less than 180 degrees. So the op amp is always stable. But practically we find several capacitors existing at several points of the op amp. All these capacitors represent different break frequencies and the phase angle will be always greater than 270 degrees, which leads to instability in the operation of the op amp, which may cause oscillations in the op amp circuitry. So we have to consider the frequency compensation techniques in order to achieve the frequency stability. First of all, let us consider the frequency response of the uncompensated op-amp circuitry. Now, let us consider the magnitude response of the open loop op-amp circuitry, and here let us consider there are 3 break frequencies, and the below figure shows the magnitude response of this uncompensated open loop op-amp. The gain of the open loop op-amp with F1, F2, F3 is given by A equal to AOL by 1 plus JF by F1 into 1 plus JF by F2 into 1 plus JF by F3, where F1 is less than F2 is less than F3. For a typical op-amp, the open loop gain A is equal to 90 dB and it is flat up to F1. Let it be 200 kHz as shown in figure. The first break frequency is F1, and from F1 to F2 it rolls off at the rate of minus 20 dB per decade. That is, gain decreases by a factor 10 when frequency becomes tenfold. Now, F2 equal to 10 F1 equal to 2 MHz, and at F2 A equal to gain at F1 minus 20 dB, that is 90 dB minus 20 dB equal to 70 dB. From F1 to F3 the gain falls by 40 dB per decade, and F3 equal to 10 F2 equal to 20 MHz, and at F3 gain equal to 50 dB. After F3 the gain rolls off at the rate of minus 60 dB per decade as shown in figure. At high frequencies, each corner frequency produces an additional phase shift of minus 90 degrees to the open loop gain. Here 3 corner frequencies are existing, so total phase shift is 270 degrees. Now let us consider the magnitude response of the closed loop op-amp. When negative feedback is used to get gain equal to 80 dB, its projection falls on minus 20 dB per decade section of the open loop op-amp curve as shown in figure, and hence maximum phase shift of minus 90 degrees exists when gain equal to 10,000 and the amplifier is said to be stable. If gain equal to 1000, that is AV equal to 60 dB, its projection falls on minus 40 dB per decade. Now the phase shift is 180 degrees and hence the amplifier is said to be unstable and should not be used without modifications. If AV equal to 40 dB, that is 100, its projection falls on minus 60 dB per decade section of the open loop frequency response, and the system becomes unstable and may become regenerative and may tend to oscillate. In practical circuits, normally we use closed loop gains less than or equal to 100, and hence certainly we get phase angle greater than 270 degrees, which leads to oscillation tendency in the op-amp. So we have to follow frequency compensation techniques in order to achieve a phase shift of the op-amp less than 90 degrees, so that the frequency response of the op-amp becomes stable. Frequency compensation is applied to op-amp to get mod A beta less than 1 when phase angle of loop gain A beta equal to 180 degrees. The frequency compensation techniques are classified into 2 categories. One, external compensation, and it further divided into 2 categories. One, dominant pole or lag compensation, and other external compensation is pole 0 or lead lag compensation. Another type of frequency compensation technique is internal compensation technique. In the external compensation technique, we connect a network at the output of the op-amp, and here in the external compensation technique we will have an access to vary the component values, and in dominant pole compensation technique the transfer function of the network is designed in such a way that it is having a pole in its transfer function. From the figure we get the transfer function of the amplifier with compensation network is A prime equal to V naught by Vi equal to A into 1 by j omega c by R plus 1 by j omega c, that equal to A by 1 plus j 2 pi FCR, where omega equal to 2 pi f is substituted in the previous expression. Now the gain of the amplifier with compensation network becomes A prime equal to A by 1 plus Jf by Fd, where Fd equal to 1 by 2 pi Rc. Substituting the expression for A in the above equation, we get A prime equal to AOL by 1 plus Jf by Fd into 1 plus Jf by F1 into 1 plus Jf by F2 into 1 plus Jf by F3. Here Fd is less than F1, less than F2, less than F3. The value of capacitance is selected so that the compensated transfer function passes through 0 dB at the pole of the uncompensated transfer function A. Therefore, Fd equal to F1 equal to 1 by 2 pi Rc, and the capacitor is designed such as C equal to 1 by 2 pi R F1. The advantages of this particular compensating technique are the noise immunity of the system is improved since the noise components outside the bandwidth are eliminated. It is also having a disadvantage. It reduces the open loop bandwidth drastically. Now let us consider the pole zero compensation technique. Here the network connected externally to the op-amp will be designed in such a way that its transfer function contains one pole and one zero. The pole zero compensation network is shown in figure. The transfer function of this compensating network is given by V naught prime by V naught equal to Z2 by Z1 plus Z2, where Z1 equal to R1 and Z2 equal to R2 plus 1 by j omega C2. Now substituting the values for Z1 and Z2 in the above expression of V naught prime by V naught, we get V naught prime by V naught equal to 1 plus Jf by F1 by 1 plus Jf by F naught, where F1 equal to 1 by 2 pi C2 R2 and F naught equal to 1 by 2 pi C2 into R1 plus R2. Now this compensating network is connected to the op-amp as shown in figure. If A is the gain of the uncompensated op-amp, then A equal to V naught by Vi. Now the gain of the compensated op-amp is given by A prime equal to V naught prime by Vi, that equal to V naught prime by V naught into V naught by Vi, that equal to A into 1 plus Jf by F1 by 1 plus Jf by F naught. Substituting the expression for A in the above expression, we get A prime equal to AOL by 1 plus Jf by F1 into 1 plus Jf by F2 into 1 plus jf by f3 into 1 plus jf by f1 by 1 plus jf by f0. Now the simplified expression of A prime is AOL by 1 plus jf by f0 into 1 plus jf by f2 into 1 plus jf by f3. In the above equation, the frequencies are related as 0 less than f0 less than f1 less than f2 less than f3. In the design, the following points are considered. R2 and C2 are selected in such a way that the 0 of the transfer function is equal to the pole at the corner frequency f1 of the uncompensated op amp. Hence, the compensated op amp, the 0 cancels the pole at f1. The second point that is to be considered in the design is the value of R1 is selected in such a way that the pole of the compensating network at f0 equal to 1 by 2 pi C2 into R1 plus R2 makes the gain of the compensating op amp to pass through 0 dB at the second corner frequency f2 as shown in figure. In the dominant pole compensation technique, the pole exists at first corner frequency, whereas in pole 0 compensation technique, the 0 is at f1 and pole is at f2. Therefore, the compensation gain function goes through 0 dB at the second pole f2 of the uncompensated gain function. Therefore, in pole 0 compensation technique, bandwidth improvement clearly takes place with a value f2 minus f1. In the internal compensation technique, we have the network, that is compensating network, fabricated on the chip itself. That is, in internal compensation technique, we won't find any access to vary the component values of the compensating network. Miller effect is used to get internal compensation. A feedback capacitance C2 is added around the intermediate stage of the op amp to increase the gain of the intermediate stage due to the Miller effect. Thus, large capacitance required to narrow band the amplifier can be realized by fabricating a small capacitor across the intermediate stage of the op amp as shown in figure. In the figure, the current I0 is the current coming out of the first stage and is given by I0 equal to Gm VID by 2, where Gm is the output conductance of the first stage. Applying KCL at node A, we get I0 equal to II plus I. Neglecting the base current II, because II is very less than I, we have I is approximately equal to I0. The current through Cc is given by I equal to minus j omega Cc V0 for sinusoidal excitation. Therefore, Gm VID by 2 is equal to minus j omega Cc V0. Now, the unity gain bandwidth frequency Ft can be related to Cc by setting f equal to Ft at mod A equal to 1. Therefore, we have V0 by VID equal to Gm by 2 into 1 by minus j omega Cc. Therefore, at omega equal to omega t, we have omega t equal to Gm by 2 Cc. That implies Ft equal to Gm by 4 pi Cc. The 741C op amp is having the special feature of internal compensation, and here the capacitor Cc is having a value of 30 picofarads. So, in this session we discussed about various frequency compensation techniques of the op amp.